Hello, my name is Kamil Khadiev. I'm from Kazan Federal University. I'm happy to present you our paper joined with Maxim Yagafarov. That is the fast algorithm for online K-server problem on trees. First, I tell you about definition of online algorithms, then about the problem itself, K-server problem on trees, and finally present you the idea of the fast algorithm. So, the online minimization problem is the problem where we accept m variables, that is input from some set of possible inputs, and for any output y1, ym, that corresponds to input I, we can define the cost function, cost IO, that is cost of this output for the presented input. Output O prime is optimal if the cost is minimal. Our goal is to construct an algorithm for the online minimization problem such that computes some output y1, ym on the presented input, but there is a restriction. Restriction is the following. The ith input can depend only on the previous, the ith output can depend only on the previous input variables. So we should output variables on some kind of online fashion. That means that we don't know future inputs, we know only the past input variables. So we assume that there is some optimal algorithm that is offline. That means that it can output a variable yi depends on all input variables, so it can read all input and compute output variable. And if it is the best offline solution and optimal, we called it opt-I. We assume that it can output this optimal output that is that reaches minimal cost. And if we have this one, then for an online algorithm, we present the main measure of quality, that is competitive ratio. We call an algorithm A, we call it C competitive if there is constant alpha that is positive, such that for any input from set of possible inputs, cost of output that that was presented by our algorithm is less than C times cost of output of optimal algorithm plus alpha. So it means that ratio between cost of our online algorithm and optimal algorithm is at most C. So let us present the problem K server on tree. We have a tree with n vertices, and we associate it with some tables in restaurant, for example. And we have k agents. Each agent stay on some vertex, maybe two agents on one vertex. So these agents can serve some queries. We assume that we have a query on vertex number q, and we should serve it. So what does it mean? It means that one of these agents should come to this vertex q. But other agents also can move. We haven't any restriction on moving other agents, but at least one agent should come to this query vertex. And what is the cost of output? The cost of output, so one query, one input is one index of querying vertex, and the output is the new positions of our agents. And the cost of this output is the total distance that all agents moving for all queries. We have m queries. For each query, we move agents, and sum of all distances that all agents moves on all queries is the cost of our output. In online fashion, we should move agents after coming each query, and this moving should be done before the next query. Yeah, xi is the index of ith query, and yi is the new positions of our agents. The new position is such that at least one of them should come to the query. Okay, there is no solution that is k competitive. The solution is the following. So we have a query queue. For each agent, we say that an agent is active if there is no other agent on the path from this agent to the query. Here also this one is active if there is no other agent on the path to the query. But this agent is inactive because there is another agent on the path of to the query. So it means that this agent cannot reach the query earlier than this one. So on each step, what we do, we move all active agents on one position to the query, and after that we also again check which one is active, which one is non-active, and again, we move all actives one step closer to the query, and so on. At least after that, at least one agent will reach queue in the end of this process, and it will be only one if the smallest distance from queue to any agent is the unique. If there are two agents with the smallest distance to the query, then there are two or so on. Okay. It is a competitive algorithm, and it is the best one. But researchers, when implement this algorithm, don't pay attention to the time-effective implementation. So the naive implementation that just searches the distance, check the distance, check which one is closer, and so on, check the active or inactive. This solution needs constant time preprocessing, but each query requires O of n time complexity. There is another more time-efficient solution that requires longer, slower preprocessing. That is n log n, and time of query processing is k squared plus k log n. So the query processing is much faster. You can see, but processing is slower, but it is already better than naive solution if there are at least log n steps, log n queries. And we present a solution that is our solution has the following properties. Preprocessing is O from n, and query processing is k log n squared. So you can see that it is better than naive algorithm already if we have at least one query, if we have more than one query, because preprocessing time is equal to the one query processing time. But comparing to this one, this preprocessing is faster, but query processing is faster only if k is at least log n squared. So let us present idea of the algorithm. We discuss processing of a query queue. Firstly, we sort all agents by their distance to the queue. We can compute distance from V to Q if we firstly compute distances from the first vertex to each other vertex, and can compute LSA of two vertices. In that case, if we compute it and store it, firstly, then we can compute distance between any two vertex in constant time, and it means that the sorting of the agents takes k log k time. Okay, after that, we assume that V1, Vk are in sorted order. We can be sure that the first server on V1, first agent, processes the request queue. Yeah, because it is the closest agent to the query. So for the first vertex, we color all vertices on the path from V1 to Q to color 1. Here, his color is 1, so and we mark it by red color. All of them are red. So for all other vertices, for all other agents, what we do? We search the closest colored vertex on the path from this agent I to the query queue. Here, for example, the closest colored vertex is this one. So we know that because this distance from one first agent to the query less than this distance, then we know that agent 1 comes to this vertex earlier than agent 2. That's why this agent will be inactive in this moment, and it will be inactive because of this agent, because it is closest color. So color means that this vertex will be visited by the agent. So this vertex will be visited by agent 1. That's why they have color 1. This vertex, some other vertices will be visited by agent 2. They will have color 2 and so on. So this is the closest colored vertex. And what we do, we want to color all the required vertices by color 2. How many vertices will it be? It is if this vertex is W and the distance between V1 and this vertex W is 1, then it means that agent 2 can move only to one vertex on the path from V2 to Q before it becomes inactive, because this first agent will come to vertex W. So we color these T vertices on this path to color 2. And so on, we continue. For example, this one already inactive, and we color on one vertex by color 3. So on, we do it for all agents. We can do it for each agent, we can do it in logarithmic square time because of heavy light decomposition and symmetry data structures that we construct for these three. It is the processing of query, and pre-processing required preparing some data structures and some stored information for heavy light decomposition, for LCA, for segment trees and distance procedure that compute this distance from some two vertices. Okay, finally, the existing implementations naive have such complexity. The existing fast implementation have such complexity, and new complexity is this one. So it is better than naive implementation if k is asymptotically less than n over log n square, or number of queries more than constant. And it is better than this fast solution if k is bigger than log n square. That is also suitable and possible cases in practice. Thank you for your attention.